All right, so we'll jump into this warm-up. It says place a star next to each set of side lengths that can make a triangle. So we have to go back and revisit that whole idea of what can or cannot make a triangle. So you remember we had our sticks, and we said that if two sides of the triangle are the same as my largest side, that no longer makes a triangle. So does that ring a bell to you? And we use that rule. We use that rule to come up with all kinds of triangle inequalities. And that was when we were missing a side of the triangle. When we were missing a side of the triangle, we came up with rules that let us find the boundaries for that x value, high and low, saying that the sum of any two sides of a triangle have to be greater than the third side. So when I look at these ones, I was given all three sides. So it's a little bit of a difference from what we did here. Instead, I know what my biggest side is, and as long as the sum of my other two sides is greater than that third side, I know I have a triangle. So because 13 is bigger than 10, yes, I have a triangle.
So is this the right way? So I just took 82 of the numbers and add them together, get the biggest one, minus them, get the lesser one than x. Would that still be correct?
So you don't need to do that subtraction part because we already have all three sides. I don't need to know that lower boundary because it already exists. I just need to make sure that when I add two sides of the triangle together, it's bigger than this.
So it would be better if I do like the smallest.
So you identify your biggest side. So here they're both 12. So there's no such thing as a largest because these two are the same. As long as this is true, then yes, you have a triangle. Now this one is interesting. So yes, I have a triangle here. Not a problem, right? So when we look here, if my largest side is 21, is 8 plus 12 greater than 21? That's not true. So therefore, this is not a triangle. So notice I skipped the one in the middle. Why do you think kids have a harder time with this one?
Fractions.
Yeah, because you all are scared to death of fractions. Do not be afraid of fractions. If you didn't get your calculator, go get it now. Because on your calculator, you have the ability to do fractions easily. All right, so when we're talking about each of these fractions, our calculator, all you need to do is 1 divide by 2, 1 divide by 3, 1 divide by 4. When you do that math, it shows you very clearly what each one is worth decimal-wise. Now, our hope is that you recognize that the larger the number in the denominator, the smaller the value of the fraction. Think about that. Do you want half of a plate of brownies or 1/10 of a plate of brownies? You definitely want half. Actually, we'd like to have all the brownies. So why talk about a fraction at all? So when we look at this, we recognize that 1/2 is our greater value. So I need to make sure that 1/3 plus 1/4 is greater than 1/2. Doing fractions on the calculator is easy. Fractions are just little mini division problems. So 1/3 plus 1 divided by 4. What you have here is an order of operations problem. Your calculator knows to do this division problem first, this division problem second, and then add them together. So as long as what we have here is greater than 1/2, yes, you have a triangle. Explain to me why I don't need to do any math to this guy at all. Yeah, he is equilateral. So yes, I have a triangle, and I know that he is equilateral. Of course, if I know he's an equilateral, then he's also equiang. You know he's also equiangular. All right, so this one's not a triangle. We don't have to worry about classifying him. This one we got equilateral and equiangular, easy peasy. Talk to your group mates about classifying A, B, and C by sides, and then talk about whether or not you can classify it by angles. On your mark and set, talk. All right, do we agree? A and C are scalene because I have 3 different side lengths. B is going to be isosceles because I have 2 congruent sides. Now, when it comes to classifying by angles, other than this one, which I know everything is a 60-degree angle in that one, I don't know anything about the other ones. Without having any kind of picture or drawing or any kind of angle information, I don't have the ability to classify by angles. And I'm going to add a big yet onto that conversation because after our quiz today, we're going to talk about how it is that we can use a Pythagorean theorem to help us out with that. All right, so that's a little foreshadowing for what's coming on. All right, take a look at this figure on the back. Solve for each of the missing angles. And then I want you to classify each of the triangles by sides and angles. List the figures in order from shortest to longest. On your mark, set, talk, go. All right, come back. Let's talk about each of these triangles. And I want to make sure that we're on the same page with how I figured these out. So my first thing that I did was I noticed that these two were isosceles. So if this is 62, then so is this. So I know that angle A degrees and this 62 degree are the same because of the isosceles angle theorem. So when I add 62 and 62 together, subtract it from 180, I get 56. But then I notice this little box here that tells me this is a right angle. So I know that 90 minus 56 is 34. Once I have this angle, I come down here and I recognize that these are a linear pair, and linear pairs are going to be supplementary. So I know that 180 minus 62 is going to be 118. Now I can double check myself because this exterior angle is going to be equal to the sum of these two together. When I add 56 and 62 together, makes me feel good. I have 118, so I know I got the right answer there. When I'm solving for angle B, I've got 2 choices. I can use my 34 and 118 angle, add them together, subtract from 180, or I can use my right angle, my 62 degree angle, and then figure out that 28 and 62 have to be complementary because they are the angles of a right triangle. So whether I think about solving angle B by getting this big triangle here or using this obtuse angle, I'm good to go. ABC is obtuse and scalene because this is greater than 90 degrees. And all of my angle measures are different, which means all my sides are different. ACD is an acute isosceles. It's isosceles because these 2 angles are, these 2 sides and base angles are congruent. And everything is less than 90 degrees. That's why it's acute. I know that ABD is a right triangle because of that box. And I know it's scalene because these 2 complementary angles have different measures. So this next part is kind of important because when you list the sides in order from shortest to longest, I don't have a side that's common between these 2 triangles. So when we did this before, there's a shared side that was the largest of one and the biggest of another, and that's not the case here. So because CD is my smallest, and AC and AD have the same measure, I don't know where AC fits in realm to the other one, so I'm going to list them all separately. ABC, for triangle ABC, AC is the smallest, and then BC, and then AB. And then for my largest triangle, I know that the side opposite my right angle, my hypotenuse, is definitely my largest side. My side opposite my smallest angle is my shortest side, and then AB is in the middle. Questions on the warm-up? Yeah, Rachel.
How did you do ACB again?
ACB, this one,
Yeah.
when I list my shortest side, I know that this is my smallest angle. So my shortest angle has to be, my shortest side has to be,
Oh, okay, thank you.
make sense? Okay. Go ahead and take out your homework that you have from last class. And go ahead as a table group, compare your multiple choice for the first 8 problems. Go ahead. All right, come back. Let's talk about it. So this is the one where I do have to set up those inequalities, because if I don't have my third side measure, I have to consider a lower and an upper bound for it. I don't know where that third side fits in with 7 and 11. I don't know if it's the smallest or the biggest. So I have to consider the fact that each of the other sides added together has to be bigger than the third side. Now, these are the kinds of problems that will get you all the time. They'll list the values, and because you got that and you're solving, you're like, sweet, those are the answers. And you're like, no, they're not. Because they can't be equal to it. If they're equal to it, then you don't have a triangle. Now, back in my day, when you took a multiple choice test, if you got more than one answer, you knew something was wrong. You weren't reading the problem right. You went back and looked at it again. In your day, there's multiple selects, right? So you guys are used to that idea of having more than one right answer. So you want to make sure that you're reading carefully and paying attention to why 4 and 18 are not answer choices. All right, number 2, S is the largest. Number 3, again, I'm going to cross off 22 and 62. Number 4, when I order the sides, longest to shortest. Oh, I did it backwards, didn't I? Because it says longest to shortest. So my BC has to be my longest. And then next comes AB. And then next comes AC. Olivia, you saw that, didn't you? Go put Smarty up. This one was so confusing because you're finding which cannot be the length of the remaining side. So if 2 sides of a triangle are 14 and 8 inches, this is going to be my boundary markers. So 8 is fine, 14 is fine, 21 is fine, 6 is not fine. That's why it's the choice. Measure of angle X is the smallest for number 6, and 7, which could not be the length of the sides of a triangle because 6 plus 3 is equal to 9, which are possible dimensions. These are all no's. So the answer there is C. Go ahead. So if I add 4 and 5 together, that's 9. So the sum of any 2 sides has to be bigger than that third side. And 9 is not big enough. So if I had a 4 and a 5 and a 10, Sabrina, I'd get a triangle that no matter what I did, the sides weren't long enough to meet. I would end up with something like this. All right. On the back, A was obtuse, isosceles. B, scaling right. C, scaling acute. D, that's an equilateral and an equiangular. Make sure you get that vocabulary right. For number 2, when I solve for y, I know that 146 is my exterior angle, so these two have to add together to be equal to 146. And that's how I get y has a value of 15. Now, some people prefer to just take the long way. That's fine. They're knowing this is supplementary, and then this plus this plus this has to equal 180. That'll still work. We just do a little bit more work. If you remember your exterior angle theorem, it saves you a couple steps in calculations. As an acute scalene triangle, and when I list my sides and angles in order, there we go. For number 3, given isosceles triangle ABC with that base, when I find my measures, I know that twice 5x plus 10, because here these two sides of the triangle are congruent, so these two base angles are congruent. If x has a value of 3, my vertex angle ends up with a measure of 130, which makes it an obtuse isosceles. Real quickly down here at the bottom, 13 plus 5 is 18. That's not long enough to be a triangle. 20 and 4 is fine. 1, 1, and 2, not okay. It's not a triangle. 5, 6, 7, that is a triangle. Sound okay? Yeah.
So it was on the homework. It wasn't homework. It was on the math space. It was like a triangle that had like no equal lines, and it had like.
When you finish with the quiz, you're going to pick up this piece of paper. And this piece of paper is a review of our Pythagorean theorem. And what you're going to do is recognize that in every right triangle, your hypotenuse is opposite your right angle. Whether you put the Pythagorean theorem with c squared on the left or right, it doesn't matter. But what I want you to be able to do is identify the hypotenuse and then be able to write an equation to solve for it. So for this one, 4 squared plus 12 squared is equal to c squared. 18 squared plus 36 squared is equal to x squared. If your variable is not in the hypotenuse, make sure that you don't put it in the hypotenuse position, because then that'll help you solve for it. So after you finish your quiz, a quick review of the Pythagorean theorem. All right. I want to talk to you real quickly about this worksheet and give you a little bit of background on what we're doing. It's actually not our note sheet for today. I passed that around. So put that off to the side for now. And I do want to talk to you real quick about the Pythagorean theorem. So it's real simple. The square of the two sides is going to be equal to the square of the hypotenuse. When you're doing these problems, this side squared plus this side squared is equal to this side squared. A couple calculator tricks to help you. Whenever you want to square a number, you've got two choices. So if I want to hit 4 squared, I can hit 4 and then this button here. And that button there will add the square, enter. We'll do the calculation for you. What I prefer to do more often is this key. That's the exponent key. So if I press 4 to the second power and then press enter, this key is more functional because if I have something other than squared, I can do something to the 3rd, 4th, or 5th, or 6th power. So those two keys are going to be the ones that help you get your squared. When you add together 16 and 44, you get 160. So if it's time to take the square root of 160, your choices are, actually, you need to take the square root and put that symbol in first. That is a second function. See it in blue? See it here in blue? So you have to press this second function and then the x squared button, and that's what gives you this radical sign. When you press 160, you're going to arrow out to show that you are finished. Press enter. When we estimate the square roots of values that are not perfect squares, this is an irrational number that goes on forever and ever. The only reason it stops here is because my calculator is out of slots. If there were 10 more slots, we'd have 10 more digits. If there were 20 more slots, we'd have 20 more digits. If there were 1,375,000 more slots, we would have 1,375,000 more digits. That's what an irrational number does, goes on forever and ever. We don't have time for that. We're going to round everything to the nearest hundredth. So once you go to where you want to stop the decimal, you peek one decimal place further. If it's a 5, 6, 7, 8, or 9, you're going to go ahead and round one place value up, which is why you see 12.65 here. These two curvy little symbols here tell everybody, hey, this is an estimate. This didn't divide out evenly. So we're going to give our answers in two ways. One is an estimated value, and one is the exact value. The exact value includes simplifying radicals. We're going to continue working on simplifying radicals because I think it might be part of your algebra background that's a little bit weak. Kyle, you with us? So when I go to simplify 160, I'm breaking it down into its factors. The easiest way is just to keep dividing by 2 to find those double factors. Any double factor can come out of the radical. So this set of 2's comes out as 2. This set of 2's comes out as 2. I'm left with a 2 and a 5. No double factors there. So they stay under the radical sign. And that's how I have a 4 roots of 10. If you are a number person and you enjoy spinning the numbers around in your head, I actually prefer another method. If I think about the square root of 160, I prefer to think of this as 16 and 10. I know this is a perfect square. The square root of 16 is 4, and that's what's left. So you tell me which of the two methods do you like better? So we're going to continue talking about this. This sheet, go ahead and at the top of it, would you write the word stinger? Because when we have stinger, this is the sheet I'm going to ask you for, and the sheet that I want you to be able to have ready for me when we go. You're going to have to do it. So whether you do it now or later, up to you. But for today, I want to get busy on talking about our notes for today, which are this. Did everybody get them? Okay. So again, we'll talk about our Pythagorean theorem. And, you know, real interesting story about Pythagoras. When you get to know him, he was kind of like a hippie of his time. He was this crazy avant-garde thinker, challenging rules, coming up with different ways of doing things. Goes and studies in Egypt, and he sees the Egyptians already have this relationship figured out. He just formalizes it, slaps his name on it, gets all the royalties and the credit, so good for him, right? What he actually was more interested in is this concept of Pythagorean triples. If you go ahead, and I'll post this on Schoology. It's a funny video by a woman named Vi Hart. If we have time at the end, I'll click on it and bring her up. But it's a funny video where she likes to tell stories about where the math that we study comes from, and she does it through drawing and telling the stories, and it's pretty cool. All right, our Pythagorean theorem says that when you take the square of the two sides of the triangle, that is always going to be equal to the square of the hypotenuse. Hey, some things you need to know. Our hypotenuse is always going to be the side that's opposite of our right angle. So whether you want to highlight it or color it in red or do something, because if you take the time to make sure you get to know your hypotenuse, it's always going to be the longest side, and it's always going to be opposite of that right angle. So one of the classic proofs that you may have seen before of this right triangle theorem is if I have this side length of 3, when I talk about a 3 by 3 triangle, I end up with a triangle with an area of 9 units because 3 times 3 is equal to 9. Count them, 1, 2, 3, 4, 5, 6, 7, 8, 9 units when I square that side. If I were to take another side of the triangle, here I have a triangle with side lengths of 4. It is a 4 by 4 triangle. Then 4 times 4 gives me an area of 16 units. And I can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Those areas, when added together, are going to add to the area created by squaring my hypotenuse. So my hypotenuse is going to be the square root or the side length that is equal to this area. Here's my 9 purples, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's my 16 greens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these 16 greens and those 9 equal 25. When I take the square root of 25, I get a 5 measure for my side. Some fun facts about the Pythagorean theorem. One of the US presidents also discovered another way to prove the Pythagorean theorem. Go ahead, Google it, see if you can figure out who it is. Our Pythagorean triples are going to be defined as right triangle sets of values that work out to be whole numbers. And when we talk about whole numbers, we need to make sure that we're talking about whole values. No fractions, no a over b's, no square roots of numbers that are not perfect squares, and obviously no negatives. We can't have a negative side length. Here's where the geometry comes in. Today we're going to talk about the converse of our Pythagorean theorem, because what this now allows us to do is we can now prove a triangle is a right angle. So in our previous conversation, if it's a right angle, then this is true. In the converse, of course, you know it's backwards. If this conversation is true, then it's a right triangle. So you can say that if that relationship is true, it's a right triangle. All right, flip over to the back because this is a part that's super cool that I love. Because just like we talked about on our warm-up, it's nice to be able to look at triangle side lengths and know, hey, what kind of triangle is that? And we can talk about these Pythagorean inequalities. And when I talk to you about this, I'm going to use 3 different pencil lengths and see if this makes sense to you. So for the people watching the video, I'm referring to my golf pencil. I'm referring to my pencil or my pink pen, and I'm referring to my purple. And you can see that each of these is not the same length. My golf pencil is smaller. This is going to be my middle length, and this is going to be my longest. And here's how it works. Everybody take your fingers, and just to see what I'm doing this shape. Take your fingers and do this. See that lovely right angle that we can kind of look at and say that's definitely a right angle? If I take my pencil, it just matches about perfectly. Does yours? So if c squared is equal to a squared plus b squared, then I have a right triangle. So if you look at how this pencil fits, it looks pretty good like a right triangle. Are you okay with that? Okay. Now let's take my golf pencil. Smaller or bigger than my pink pen? If c squared is smaller than a squared plus b squared, what kind of triangle do you think I have?
Acute.
I have an acute triangle. There's my golf pencil. Now I'm taking my last pen. If c squared is longer than a squared plus b squared, notice I have to open my fingers up as wide as they can go to make that distance, to make that triangle possible. What kind of angle is this?
Obtuse.
Okay. Here is our conversation. And it helps us if we go ahead and we put c squared on the left-hand side, so we can talk about if c squared is less than a squared plus b squared, that's when I have an acute triangle. I have an acute little angle. If the distance between the tips of my fingers is smaller, notice it makes it the angle an acute angle. So c squared is smaller. All right, let's talk about what happens if c squared is greater than. Open your fingers up wide. What kind of triangle is it? This is going to be obtuse. So if you think about it in terms of this distance of c, if c is smaller than a squared plus b squared, I have an acute angle. If c squared is larger than a squared plus b squared, then I have an obtuse. All right, so let's check it out. For number 1, a, b, and c, I need you to solve for x. And sometimes x is a leg, and sometimes it's a hypotenuse. So it'll do you good if you take the time to find your right angle in each triangle. And then you take your time to find which side of the triangle, which triangle side is your hypotenuse. Because then when you write your equation, 15 squared plus x squared plus is equal to, 20 squared, then you'll need to be solving for your leg. If x is in your hypotenuse, then you know that 8 squared plus 12 squared is equal to x squared. If x is a leg, 10 squared plus x squared is equal to 21 squared. So go ahead with your group mates, talk about solving them, and I want you to find your answers 2 ways. This says leave your rational values as simplified radicals, and I want you to estimate to the 100th. All right, off you go. Okay, so when you look at each of these, when I set up my equation and I do 15 squared, x squared, I subtract, you'll see the difference between my 2 answers. Now, in Stinger on Friday, we're going to talk more about simplifying radicals. But the people who are good at spinning numbers around in their head do better at this. And everyone has the capacity to spin numbers around in your head. The choice is, are you practicing or not? So when I look at 175, I know 25 goes into that. How do I know that? It ends in a 5. So you think about it, $1.75 is going to be 7 quarters, right? 4 for the dollar, and then 3 more for the 75, right? So I know 25 goes into that. 25 is one of my best friends. He's over there behind Christian. He's a perfect square. These sets of numbers, king and blue, these are my best friends. These are the friends I look for in every math problem. Just like you look for your best friends in the cafeteria when you go to lunch, you look for your best friends at the pep rally, you look for your best friends at the football games, volleyball games, basketball games. I look for my best friends in every math problem I approach because they make my life easier, my cubes and my squares. 175 is 25 times 7. I can take the square root of 25. He comes out of the radical, 7 stays inside. When I go to solve for x here, I get x squared is equal to 208. I take the square root of that. It's about 14.42. When I go to simplify 208, that's 16 divided by 13. So when I take the square root of 16, it comes out as 4. The 13 stays inside. When I do my math here, I end up with x squared is equal to 341. 341 is 11 times 17. There's no perfect squares in that. So I leave him as is, but then I can estimate that.
For me, I did the same format as A, so I did 8 plus x, no, 8 to the second power plus x to the second power.
You can't do it that way because x is my hypotenuse. That's why we took the time to say this is the right angle, this is the hypotenuse, so x. Yeah, see how this is a leg and that's the hypotenuse? Good catch. All right, number 2, which of those triangles are a Pythagorean triple? None of them. None of them. Because every single one of them has a value as an output that's not a whole value. You're counting numbers. Think about that real number system. The most specific category on the way inside, what you learned as a little baby first. You didn't learn to count to 0. Nobody said to you, how many cookies would you like? And you said 0. You always started with counting 1, right? So we call them your counting numbers. You start with 1, your 1 shoe, 2 shoes, right? So your counting numbers are going to be your whole values, only positives, no negatives, no fractions, no irrational numbers, and no zeros. That's what we call a Pythagorean triple. The most famous Pythagorean triple is this one right here, our 3, 4, 5 triangle. All right, last part of this notes goes back to what we were talking about with our warm-up. I can now look at a triangle and I can put it through the Pythagorean theorem to see if it's a right triangle or if it's an acute triangle or if it's an obtuse triangle. So right now, get in the habit of either highlighting or drawing in another color your longest side. And you need to know which side is your longest side. So what you're going to do is you're going to set up a Pythagorean equation. 39 squared plus 80 squared. But instead of it having being equal to c squared, we're going to put c over here. And we're going to look at, is c bigger than, is c smaller than, or is c equal to? We don't know. Same thing here. 4 roots of 35 squared is going to have some relationship. Maybe bigger, maybe smaller, maybe equal to.